Very good morning to everyone. In this lecture, EC8652 wireless communication. In this session, we are going to discuss about the topic minimum shift keying. So, it is one of the digital modulation techniques in fundamental digital communication. It is a type of continuous phase frequency shift keying that was developed in the late 1950s and 1960s. Similarly, the offset QPSK, the MSK is encoded with a bit alternating between the quadrature components with the Q components delayed by half of the symbol period. So, it is a special type of continuous phase frequency shift keying, that is a CPFSK technology. Here the peak frequency deviation is 1/4 of the bit rate. So in this continuous phase frequency shift keying is the modulation index and or if the frequency spacing is equal to the minimum shift keying, that is called the MSK. So the frequency spacing, that is a lambda f, is a minimum shift that permit the concurrent detection of the orthogonal signals. On the other hand, the MSK is also said to be a continuous phase, that is a frequency shift keying with the modulation index of m. So here we can see the MSK is a special form of binary continuous phase frequency shift keying. So the modulation index h is equal to 1/2. Now the phase of the carrier in the interval nt less than or equal to the time period of less than or equal to n plus 1 into the time period. So the phase of the in space quadrature components in space of the signal pi of t and I is equal to 1/2 into pi summation of k is equal to minus infinity to n minus 1 time ratio into the in space information ik plus pi inq of t minus nt. So this expression can be the carrier in the interval of nt less than or equal to t, and the time symbol of time period is less than or equal to 1 n plus 1 t time period. So the modulated carrier signal is s of t is equal to a cos of 2 pi fct. It is a one of the carrier signal plus pi n plus 1/2 pi in t minus n t divided by t. So this is a in space on the quadrature phase of the two sequenced signals. In this, it is one of the time representation of the input signals. Now we can move to the continuation of MSK. The expressions indicate that the binary of continuous phase frequency shift keying, a signal can be expressed as a sinusoidal having one of the two possible frequency in the interval of the same time period. That is, what are the intervals? Nt less than or equal to t less than equal to n plus 1 of t. So the frequency, how to find out the frequency? So the definition, these frequencies as the f1 is equal to fc plus 1/4t, and f2, that is the second carrier frequency of the signal, fc minus 1 divided by 4t. Then the binary of continuous phase shift keying signal may be written in the form of si of t is equal to a cos into 2 pi fct plus pi n plus 1 plus 2 n pi of minus 1 power of I minus 1. So the I indicates the 1 and 2, the continuous varied the signal informations. So the MSK, let us, the Si of t is continue to divided into S1 of t and S2 of t can be divided into two signals and they are orthogonal to each other. Then the S1 of t and also the S2 of t is equal to 0. So the MSK techniques also termed as a fast FSK. So the MSK is highly suitable for cellular mobile communication. Now we can move to the continuation of why binary continuous phase frequency decaying with h is equal to 1 by 2 is called a minimum shift decaying. Okay, so h is a modulation index of h is a 1 by 2. So the because the frequency separation lambda f is equal to f2 minus f1, that is a in space and out of phase is equal to 1 by 2 time period, and the delta del of f is equal to 1 by 2 t. It is the minimum frequency separation that is necessary to ensure the orthogonality of the signal s1 of t and s2 of t over a signaling interval of length t. So the space in the nth signaling interval in the space state of the signal that result in phase continuity between the adjacent intervals. So we can consider the m bit stream. The MSK signal can be expressed how to the m bit stream of the MSK signal, that is a nth signal interval. So the x of msk of t is equal to summation of I equal to 0 to m minus 1 or n minus 1 into the n1 of t and p of a cos omega ct plus nq of t, that is a in space and quadrature phase, ni of t and also the nq of t into the a minus tb, that is a bit duration in the carrier signals. Now we can move the minimum shift keying. It is considered as a continuous phase shift keying signal which is defined for the interval of 0 less than t less than tb, that is a bit duration. In these conditions, in this interval of these conditions, the signal s of t is equal to the, in case the signal, whenever the signal symbol value is 1, the root of 2 eb divided by tb cos of 2 pi f 1 of t plus pi of 0. This is a symbol 1 duration of the MSK modulated output signal, and then symbol 0 root of 2 eb divided by tb cos of 2 pi fct plus pi of 0 for symbol 0. So in this expression the EB is denoted as a transmitted signal energy per bit, and TB is denoted as a bit durations, and pi of 0 is denoted the value of the phase at a time is equal to 0, and sums up the past history of the modulation process up to the time t is equal to 0 in the 0 to 1 or 1 to 0 in the timing interval of their time bit durations value. So the ni of t and nq of t, that is in space and quadrature phase, are odd or even bit of the bipolar data streams, and they feed the in space and quadrature wind as a modulator. It is also the worth nothing that there is a variety of basic pulses used in the MSK, such as that the being many variations of MSK. For example, the MSK utilizes the alternative positive and negative half cycle of sinusoidal waves as a basic pulse shapes. The MSK is a best to obtain the spectral efficiency of the signal. Now we can move. The another useful way of representing the continuous phase frequency decaying signal S of t is to express it in the conventional form of an analog angle modulated signal. So the angle modulated signal is S of t of the input signal is declared to root of 2 eb divided by tb cos 2 pi fct plus pi of t. Here the pi of t is the phase of the signal in the S of t, that is the time representation of the signal in the input of the MSK. When the phase pi of t is a continuous function of the time, we find that the modulated signal S of t itself is also continuous at the all times including the inter-bit switching times. Now we can move the phase, that is a pi of t of these continuous phase signals increases or decreases linearly with the time during the each bit duration of the bit durations. So the pi of t it is represented as a pi of 0 plus or minus pi h of tb into t. So here the pi h of t into the t is declared on the carrier signal or in the in space or out of phase in these durations. What are the durations? 0 to time period, time durations. So the pulses, what are the pulses? The minimum pulses. So the pulses are signed as corresponding to sending the symbol 1 or 0. We can find out the carrier signal F1. So F1 is equal to Fc plus H of 2 TB, and F2 is equal to Fc minus H of 2 TB. Now we can move the deviations. Here the MSK, the H is referred as a deviation ratio. With H is equal to, already we can say 1 by 2. So the frequency deviations equal half the bit rate. This is a minimum frequency spacing that allows two FSK signal representing the signal symbol 1 and 0 be concurrently orthogonal. At this time the TB is equal to pi h for symbol 1 and minus pi h for symbol 0. The sending of symbol 1, it increases the phase of the continuous phase shift keying signal S of t by pi h radians, whereas the sending of symbol 0, it reduced by the equal amounts. So the MSK, that is a minimum shift keying phase release of the code, that is a 110100. This is a H of 1 by 2 of the in space and out of phase components. From these expressions, the continuous phase signal S of t can be represented as the bit duration. In bit duration is equal for different intervals. So the root of 2 EB divided by TB cos of theta of t cos 2 pi fct minus root of 2 EB TB sin theta of t sin 2 pi fct in the in phase and out of phase components of the carrier signals. First carrier signal is indicated as the cos functions and sine functions. So the S1 of cos 2 pi fct minus SQ I sin 2 pi fct, that is a SI is denoted as a in space components of the input signal, and SQ is a quadrature phase shift of the continuous phase shift keying signals. Now in this in space components SI with the deviation ratio H is equal to 1 by 2, that is a theta of t is equal to theta of 0 plus or minus 2 EB. So as a result, it hold the theta of t in the interval of minus TB to 0. It expect the algebraic sign is not necessary to same in the both interval. Hence the phase pi of 0 is 0 or pi depending on the past history of the modulation process. In the polarity of the cos theta of t depends on only on the regardless of the sequence of ones and zeros transmitted before or after the time period is equal to 0. Now we can move to the in space components SI of t. It consists of off cycle. So off cycle cosine pulses. How to define? The in space components of S of t is a MSK signal to the root of 2 EB divided by TB cos of theta of t is equal to root of 2 EB divided by TB cos of theta of 0 into the cos of pi divided by 2 pi into t. So the 2 pi into TB is a time duration in these the in space components of the positive or negative cycles. So the minus TB is less than or equal to t is less than or equal to t positive TB. So the components of the in space signal is plus or minus the root of 2 EB divided by TB, and also the cos function of pi divided by 2 TB into t, whereas pulse plus or minus is signed as corresponding to the theta of 0 is equal to 0 or theta of 0 is equal to pi, that is 0 to pi values. Now we can move to the MSK. Signal may assume any one of the four possible forms. The phase, that is the phase of theta of 0 is equal to 0 and theta of TB is equal to pi by 2. It is corresponding to the transmitter symbol 1. So whenever the symbol 0, the phase of the theta of 0 is equal to pi and theta of the time bit duration is equal to pi by 2. And whenever the symbol transmitted symbol of 1, the phase is a pi or theta of TB is equal to minus pi by 2, and also the corresponding the transmission of the symbol is 0. The phase theta of 0 is equal to 0 and theta of TB is equal to minus 2 pi minus pi by 2. Now, in these functions, we can find out the orthogonal basic function of the in space and the out of phase components in the pi 1 and pi 2 of t. Let us see the define the orthonormal basic functions, that is a pi 1 of t and also the pi 2 of t. Let us the two functions is a different correlation functions in the sinusoidal output signal in the MSK. From this signal, that is S of t is equal to S1 of pi 1 of t plus S2 of pi 2 of t. That is a coefficient factor of S1 and S2 are related to the phase states of pi of t, pi of 0 and pi of tb respectively. Now, in this S1 and S2 is identified to mention the MSK outputted signal in the root of EB cos of theta of 0 in the duration of minus 2 plus sine functions in the interval, and also the sine S2 is a secondary signals of the minus root of EB sine theta of TB 0 to 2 TB. So both integral of are evaluated for a time interval equal to the twice the bit durations, and both the lower and upper limits of the product integration used to evaluate the coefficient S1 are shifted by bit duration with respect to those used to evaluate the coefficient S2. The time interval, that is a 0 to TB, for the secondary signal, for which the phase states the theta of 0 and theta of TB is defined, is common to both integral. Now, what are the concurrent detection of the MSK signal? In this case, the additive white Gaussian noise channels, the received signals is given by x of t is received signal is equal to s of t plus w of t. So here the s of t is a transmitted MSK signal and w of t is a sampled function of the white Gaussian noise process of the zero mean and power spectral density n divided by 2. So we can find out the optimal decision of the theta of 0. Here the x1 is equal to integral of the duration of minus tb divided by tb x of t pi 1 of t dt is equal to s1 plus w1. That is a in bit duration of the symbol is a minus 2 plus. So the x 1 greater than is 0 is the theta of 0 is equal to 0, and also the conditions of x1 less than is equal to 0, the theta of 0 is equal to pi. Now the MSK is a optimum detection of theta of TB, whereas the x2, how to find out the x2? The x2 greater than 0, the theta of TB is equal to minus pi by 2, and also similarly the x2 greater than is equal to 0, the theta of TB is equal to pi by 2. So we can find out the error probability of the MSK signal. The error probability PE is equal to 1 by 2 function of the root of EP divided by N naught, which is exactly same as the binary PSK and QPSK modulation techniques. Now we can see the transmitter section of the minimum shift keying. Here the cos of 2 pi fc is a input signal, sinusoidal input signal is applied to the filter, that is a narrowband filters, baseband narrowband filters. It applied to the summation of the summing amplifier and also the multiplexer. So the both signal f1 and f2 is a in space and quadrature phase components of the two different phase of the signal is a pi 1 of t and also pi 2 of t is equal to summing the summing amplifier plus and plus values. So we get the MSK signal, modulated MSK signal output, and also we can see the MSK receiver. It is one of the concurrent MSK receiver. The modulated MSK output signal is applied to the multiplexer, that is a pi 1 of t and pi 2 of t. So the x of t is divided into pi 1 of t and pi 2 of t, and the in-space channels, that is the integration level of the individual channels. The first pi 1 of t is integrated with the duration of minus db to db into dt, and then the pi 2 of t is integrated the quadrature components of 0 to db in dB, and then we can decide the decision devices. In this threshold value of zeros or ones, we can decide the signal representation to the estimation of the signal is to apply to the logic circuit for interleaving the phase decisions circuits, and also we get the original input signal, that is a original output binary sequence. Thank you for watching this video.